some reaction, it's the enthalpy involved with that. I don't know how to explain it other than that. Are there questions on that? Okay. Delta H of fusion, we'll talk about that one in a second. Same with vaporization. Formation is the amount of heat produced or released from a formation of 1 mole of a substance from its standard components. So that would look like something like, if you were to form C5H14, it'd be the enthalpy involved with reacting hydrogen gas, and you'd need 7 moles of that. And you'd want to react it with carbon, solid, and it'd be 5 moles of that. So whatever the enthalpy of this reaction is, that would be the enthalpy of formation for, pentane. So that's how you do delta HF. Okay, and then there's delta H of solution. So that's like the enthalpy due to solvation. That's when ions split up and then the water bonds to those ions. Any questions on any of those? Yeah.
Just to clarify, if there was a problem about condensation or about melting, the enthalpy of fusion has to do with melting.
Yeah, so that's actually right here. So this is how I like to show it. So that red line would be represented by the delta H vape, which is the vaporization. So that's the amount of energy required per mole to change a liquid into gas. Or if you did the reverse, it'd be the negative of the gas in the liquid, so condensation. But you still use the vape. And then for freezing and melting, that's going to be delta H fusion. And if you had to do a problem like this, you just want to check your sign and make sure that if you're going from ice to water, you use one sign. And if you go from water to ice, you use the opposite sign. Any questions on that? Yeah.
So is it always like negative or positive going up and negative going down?
Yeah, typically, because if you think about it, you have to put in energy to a liquid to vaporize it, right? You're not going to, if you want to vaporize water, you're not going to cool it off. So it's usually going to be positive. And same for a liquid or a solid to a liquid. Okay, good on that. So we're going to go over some problems associated with that now. Yeah, moving. No, I think this is it. Okay, roll it down. Okay, so use enthalpies of formation to calculate the enthalpy of reaction for 4 hydrogen gas molecules plus 1 CO2 gas molecule, giving you 1 methane and 2 waters. And these are the delta H of formation that each of those. Can you guys all read those? No? Okay. CO2 gas is negative 393 kilojoules per mole. Water, liquid, is negative 75. And methane, CH4, is negative 242. Good? Okay, so just take a minute and try to do that one. In this case, just assume because you might say, so you do the product, sulfuric acid, he said potassium sulfate. Yeah, something like potassium sulfate. I think that's. So this okay. Yeah, good question. All right, you guys good or you want a minute? Yeah? Okay. So who got it and wants to walk us through it? What? Yeah? All right, quiet down, please. So what'd you do?
It's the sum total of the products minus the sum total of the reactions.
Yeah, perfect. So delta H reaction, I think this is on your equation sheet. So delta H reaction of any reaction is equal to the sum of the delta HFs of the products minus the sum of the delta HF of the reactants. Okay, so in this case, your products are methane and water. So you would just take the delta HF of methane, so that would be negative 242. And these are all in kilojoules per mole. I just ignore it right every time. So that would be negative 242, and you're adding the enthalpy of water twice though. So you add 2 times negative 75, and you're going to subtract the sum of the reactants. In this case, it would be carbon dioxide. What about hydrogen?
That's its natural state.
Yeah. So if you get elemental compound in its natural form, the delta HF is 0. For those of you listening, that's really important.
Hey, if you guys could quiet down, actually, that'd be great because otherwise we can't hear the recording.
So the delta HF of hydrogen gas will be 0. All the diatomic gases, I would know those. It's hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So if you want to call it Dr. Hoffwinkel, I remember it. So all of these exist as diatomic gases. So the delta HFs for all of those would be 0. So this is what you get, and the answer was, did you get negative 166? 1? 75? So negative, let me plug it in real quick. Yep, 1. Cool. Questions on that? No? I think this is you.
Wait, I have a question.
Yeah.
So if there was just like a potassium ion or something, like would it have a reaction?
Like a potassium, like an ion?
Yeah.
Are you talking about like the Bohr-Haber cycle? Because there's like ionization energies, which we're going to talk about. I think
I've never seen a problem like that.
Yeah, me neither.
So like
It's usually going to be just like molecules.
What are the units on the answer?
Kilojoules.
Kilojoules?
Is it kilojoules or kilojoules per mole?
Kilojoules per mole. Yeah, you got rid of the moles by multiplying by the number of moles. So basically, this negative 242 is kilojoules per mole. I multiplied it by 1 mole. So kilojoules per mole became kilojoules. Does that make sense? And that's what this 2 is here for too, because there's 2 moles, so you multiply it by 2 moles here.
Okay, so the solubility of gases. So with this, we're talking about Henry's law. And so what Henry's law says is that the solubility of gases is determined by 2 things. And so these 2 things are the temperature. And so normally when we think about temperature and solubility, we think that, okay, in order to get something to dissolve, we want to heat it up, right? But no, actually with gases, it's a little bit different. Because think about it, when you want a gas to stay in water, you would cool it down. because when you want a gas to leave water, you want to heat it up, right? So cooler temperature means that more gases are dissolved. Remember his example about the nuclear power plant in class. When he's talking about how the fish die because there's less oxygen in the water because all that leaves because the water's heated up by the nuclear power plant. So then also the partial pressure is the other thing that changes the solubility. So think about it. When there's more gas on top of a solution, it's going to push down more and force more of the molecules of gas into the liquid. So that's how you can remember that. And so the problem associated with this, let's see here. Yeah, it's here. Okay. So, how many grams of CO2 gas are dissolved in 1.5 liters of water if the partial pressure is 2.4 atmospheres? So Henry's law says that the concentration of the gas is equal to the KH, which is a constant. So each of these constants is unique for each scenario. So CO2 in water has a different constant than nitrogen in water. And so the KH times the partial pressure. So for this problem, what I would do is I would just go, okay, I'm going to find the concentration of gas in, this will give you molar because the units right here are moles per liter atmosphere. And I'm given partial pressure in atmospheres. So that will just leave me with moles per liter. So I'll use a nice little molar right there. So right here I'm going to get the concentration. I'm going to say, okay, equals 3.4 times 10 to the negative 2 moles per liter times atmospheres. And then I'm going to multiply that by 2.4 atmospheres. Okay, so then these units cancel out, and I'm left with, the answer is 0.0816 molar, which then I can convert to grams, right? By dividing by how many? Yeah, so then I have moles per 1 liter. And then I have, how many liters do I have? How many did I say? I have 1.5. So 1.5 liters. Those cancel out right there. And I'm left with then you just do the dimensional analysis to get the grams of CO2. So you divide by 44 grams. Thank you. And you end up getting, I got 3.6 grams. Okay, 5.3. Sorry. I must have bunched it in wrong. Anyways, so does that make sense though? The two factors that affect that. So if I had had a different partial pressure here, then it would have changed that. So moving on now. Does anyone have any questions about that?
There's a question over there. Was there still a question over there?
No? Okay.
Okay, so this is kind of confusing to me sometimes. So I want to make sure everyone had this clarification. So we talked about vapor pressure and evaporation. Wow. Vapor pressure is equal to the pressure exerted by vapor molecules that have left the liquid phase. It's proportional to the amount of molecules that are present in the vapor form. And just so you guys know,